Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Today we will continue talking about the argument of a non-zero complex number. Now we will see the geometric interpretation of the argument of a non-zero complex number. M is a point with affix Zm, A is a point with affix Za, and B is a point with affix Zb. By definition, we saw that the argument of Zm is the oriented angle UOM plus 2k pi. Similarly, we can see that the argument of Zb minus Za is the argument of Z of vector AB, which is the oriented angle between the two vectors U and AB. And the argument of Zb minus Za over Zd minus Zc is the oriented angle between the two vectors CD and AB. Pay attention here, we have to begin by the vector which is in the denominator CD and then AB. And pay more attention here also, in case we have only one letter, we have to add the origin O, we write OM, and in case we have two letters with a minus in between, we write AB. Let's see some examples. Let's begin with the first example. AB and C are 3 points with respective affixes. We need to calculate this ratio. Well, if we just substitute ZA, ZB, ZC, this is what we get. Using the calculator, we get minus I. Now, we need to deduce that the triangle ABC is right isosceles with vertex B, and this is what we call the geometric interpretation of this ratio. Well, to be right isosceles means the triangle should be isosceles and should be right. Let's begin. If we just apply the modulus, if this ratio is equal to negative I, so the modulus of the ratio is equal to the modulus of negative I, which is 1. And this is nothing but BA over BC is 1, so BA is equal to BC, and BAC is isosceles with vertex B. So till now we've proved that the triangle is isosceles. Now how do we prove that it's right? We take the argument of this ratio is the argument of negative I, and we know from before that the argument of negative I is negative pi over 2 plus 2k pi. This could be done using the calculator. Well, this means that the angle BCBA, applying the last property here, so the angle BCBA is negative pi over 2, which means that the triangle is right. So right and isosceles, the total would be a right isosceles triangle. Let's see this application. A, B, and C are 3 points with respective affixes. We need to prove in two different ways that the triangle ABC is equilateral. Try to think about it. Try to do it alone. Let's see the first method. Well, to be equilateral means all the sides are equal. AB is the modulus of ZB minus ZA. If we substitute, we get the modulus of I, which is 1. AC is the modulus of ZC minus ZA. By substitution, we also get 1. And BC is ZC minus ZB, which is 1. So we can tell that the three sides are equal and the triangle is equilateral. Now for the second method, AB is 1, AC is also 1. If we find angle ABAC, this is the argument of ZC minus ZA over ZB minus ZA, and if we substitute, this is what we get, and the argument of such a number is negative pi over 3 using the calculator. Negative pi over 3 means 60 degrees, so we have an isosceles triangle having 160-degree angle, which is equilateral. Now try to choose the method that you like. Let's see some properties. Z is said to be real if and only if its argument is k pi. We saw this before, but now we're going to see it officially. Well, if the number is real, it means it's on the x-axis. We can see that its argument, which is the angle between U and OA, let's say if the point is A, would be either 0 or pi or 2 pi or 3 pi, and this is what we mean by k pi. Now, specifically, if the number is positive real, if it's somewhere here, the angle between u and OA, the vector OA, would be 0 plus 2k pi or 2k pi. And if the number is negative real, the argument would be pi plus 2k pi. So positive real, the angle is 0, negative real, the angle is pi, real, the angle is k pi. Now in case we have positive and or negative, it's preferable to add 2k pi. Now z is said to be pure imaginary if and only if its argument is 2k plus 1 pi over 2, while pure imaginary could be positive pure imaginary somewhere here where we have the red point, and in this case the angle would be plus 90 plus pi over 2, and it could be negative real somewhere here. The angle in that case would be negative pi over 2. Remember, 2k plus 1 represents the odd numbers. Now here z is said to be positive pure imaginary if the argument is pi over 2, and negative pure imaginary if the argument is negative pi over 2 plus 2k pi. Now these properties could be summarized by this table. Real number, the argument is k pi. Positive real, the argument is 2k pi. Negative real, the argument is pi plus 2k pi. Pure imaginary in general, the argument is 2k plus 1 pi over 2, odd pi over 2. Positive pure imaginary, the argument is pi over 2 plus 2k pi, and negative pure imaginary, the argument is negative pi over 2 plus 2k pi. It's very easy to memorize this table, just try to imagine it. Positive real, the angle is 0, negative real, the angle is pi, positive pure imaginary, the angle is pi over 2, negative pure imaginary, the angle is negative pi over 2, and try to add 2k pi to these answers. Just pay attention when the number is real without specifying whether it's positive or negative, or when it is pure imaginary but also without specifying whether it's positive or negative. Let's see this example. Z is 1 minus I to the power n, where n is a natural number. We need to find a small n so that z is a negative pure imaginary number. Now here the indication is that z is a negative pure imaginary, so here I always remember the argument in this case. Z is a negative pure imaginary, so the argument is negative pi over 2 plus 2k pi. Then let's try to find the argument of z. This is 1 minus I to the power n. Using the properties of argument, n becomes outside. So this is an argument of 1 minus I, and using the calculator, the argument of 1 minus I is negative pi over 4, and this is what we get. Now, argument of z is negative pi over 2 plus 2k pi from here, and it's equal to that quantity. We just put that they are equal. We try to simplify pi from here, pi from there, and pi from there. We get minus n over 4 is this quantity. Multiplying by negative 4, we get n is 2 minus 4k, where n is a natural number and k is an integer. Now here, to find the final answer, we try to find some values of k so that we can find the values of n. For example, if k is 0, n would be 2. If k is 1, n would be 2 minus 4, which is negative 2, which is rejected because n is a natural number. If k is 2, n would also be negative, which is rejected. So let's try to see when k is negative. If k is minus 1, n would be 6. If k is negative 2, n would be 10, and so on. So n is 2, 6, 10, 14, blah, blah, blah. In fact, we stop when we see that the pattern is very clear. So in this question, if you substitute instead of n 2, 6, 10, 14, whatever here, you're going to see that this number becomes a negative pure imaginary number. Let's see this application. A similar question. This is z. N is a natural number. We need to find m when z is a positive real number. Try to do it alone. Take your time. Well, z is a positive real number, so its argument is 2k pi. We try to find the argument of z, applying the properties. This is what we get. Remember, argument of 1 plus I radical 3 is pi over 3 using the calculator. Now we get this quantity is 2k pi. Simplifying pi from here, pi from there, and 6k. Now when k is 0, n would be 0, which is accepted. When k is 1, n would be 6, it's also accepted. When k is 2, we get 12. When k is 3, we get 18. Whereas when k is negative 1, n would be negative 6, which is not accepted because n is a natural number. So the final answer is 0, 6, 12, 18, and so on. Now let's see the third kind of properties for the geometric interpretation. A, B, C, and D. ZB minus ZA over ZD minus ZC is real if and only if AB and CD are parallel. So real means that the argument is 0 or pi, and an argument of 0 or an argument of pi or an argument of k pi means that the lines are parallel. Pay attention, line AB, which is the vector in the numerator, and line CD, which is also the vector in the denominator. Now also here, if ZB minus ZA over ZC minus ZA, here we have a letter in common is real. This means that the two lines AB and AC are parallel, but having a point in common means that the 3 points are collinear. Finally, this ratio is pure imaginary if and only if the two lines AB and CD are perpendicular. So, what do we get from these properties? We can use the real and pure imaginary in order to prove parallel, collinear, or perpendicular, and vice versa. So, if I want to prove that two lines are parallel, I can perform a ratio and prove that this ratio is real. This is also used in case of collinear points, and if I want to prove perpendicularity, I perform a ratio and prove that this ratio is pure imaginary. Now, to clarify the idea more and more, let's see some examples. This is the list. Remember, parallel means real, collinear means real, and perpendicular means pure imaginary. Well, we have these points A, B, C, D, and E. Calculate this ratio. What do you say about the 3 points? It seems from this question that this ratio is going to be real. Let's see, if we just substitute, we get 2, which is real. And if the ratio is real, means either parallel lines or collinear points. Since here we have a point in common, we can tell that the 3 points A, C, and E are collinear. Now verify that the two lines AD and BC are parallel. Here we do perform the ratio. ZA minus ZD over ZB minus ZC. This is what we get, which is negative 1, which is also real. This means that AD and BC are parallel. And verify that the two lines AB and CD are perpendicular. We also perform the ratio. Pay attention while performing the ratio for the order of letters. Now here we have AB, we put it in the numerator, CD, we put it in the denominator. This is what we get, which is minus 2 over 3i, which is pure imaginary. And in case of pure imaginary, applying this property means that the two lines are perpendicular. Now let's see this application. If this quantity is 7i, then EF and GH are perpendicular. Is this true or false? Try to think about it. Pay attention to the order of letters. Well, this is true. EF in the numerator, GH in the denominator, and this is pure imaginary. The second case, this is not true, this is false, because real means they are parallel, and having a point in common means that the 3 points M, N, and L are collinear. Now this case, this is also false because this ratio is neither real nor pure imaginary, so we cannot say that they are parallel, because to be parallel means that the ratio should be real. Now the last case, this is true because this ratio is a real number. Now Mira or Rima, this is what we have. A and B are 2 points with affixes so and so. We need to find the set of points M when the argument is pi over 2 plus 2k pi. Now let's see. Mira found this argument. She wrote it in this form. Then she said that AM, BM, she translated this argument into an oriented angle is equal to MA and B. She flipped both vectors. This is correct. And this is equal to pi over 2. And if the angle between MA and MB is pi over 2, this means that M moves on the circle with diameter AB deprived of A and B. This is what Mira got. Let's see Rima. Rima used the same strategy. She also translated the argument into an oriented angle, but she said that M moves on the semicircle with diameter AB deprived of A and B. And see here the difference. Mira said that M moves on the whole circle, whereas Rima said that M moves on half the circle, on the semicircle. Now let's see. If I choose a point here on the circle of Mira, in the lower part of the circle, then if it's somewhere here on this red point, in this case the oriented angle MAMB will not be pi over 2, it will be in fact negative pi over 2. So I can see that Mira's work is not correct, whereas here according to Rima's work, if we choose M somewhere here or anywhere on this blue semicircle, the angle MB, the oriented angle MAMB would be pi over 2. So we have to pay attention in case we need set of points. We saw it before that if the angle is 90, it will be a circle with diameter AB deprived of A and B, but in case we have an oriented angle, things differ, and in this case it doesn't move on the whole circle. In fact, it moves on the semicircle deprived of the extremities of the diameter.